Hi class. So this video is going to go through section 2.3 in Math 1050. So this is we're going to translate verbal expressions into variable expressions, right? So in other words, we're going to be given something in words, and we want to turn that into symbols essentially, right? Objective one is just practicing that idea. So we want to translate a verbal expression into a variable expression. And I have here table one, which is not necessarily an exhaustive list, right? In other words, it maybe doesn't contain every type of phrase that we can put into a mathematical operation, but these are some of the common ones. So I have it grouped by operation, and so you'll see the operation identified first, and then the generic phrase in the next column, and then an example of the verbal expression in the third column. And then the last column is how that correlates to a variable expression, right? So for example, you can see the very first one, the operation we're looking at is addition. Added to is a common phrase to use with addition. And so here is a verbal expression example, 6 added to y. So this translates into symbols, right, to a variable expression as y plus 6. Right, so you can see that listed here. Right, so you want to look over this table and be familiar and comfortable with each of these. I will point out some of them. I won't read the whole list, but some things to keep in mind, for example, is that with addition and multiplication, the order, doesn't matter, right? We have the commutative property of addition and multiplication, right? That we looked at in the last section. But subtraction and division, remember, don't have that commutative property, right? So the order does matter. So you want to pay particular attention to the order. So two of them that maybe seem to trip some people up, I'll highlight, is less than and less for subtraction. So notice the first one has the word less than. So if you have 7 less than t, the order actually flips when you put it into a variable expression, right? So 7 less than t means that t is like your quantity and you have 7 less, right? So in other words, it's t minus 7, right? So you can see in the last column there. Where if I remove the word than, the order ends up staying the same. So saying 7 less t is 7 minus t, right? So don't let those two be confused. Um, um, Another one that's backwards is subtracted from, right? So you can see the very next row, subtracted from. So if you have 5 subtracted from D, right, that means you're taking 5 away from D, right? So that ends up being D minus 5, right? So that order flips, in the way it's presented with subtracted from as well, right? Right, so make sure you read over those and make sure you're comfortable. Um, at the bottom of page 1, something I wanted to point out here is notice that the words sum, difference, product, and quotient. Um, these are words that mean the answer we get after doing an operation, right? So sum, remember, is what we call the answer we get when we add things, right? Difference is the answer we get. So sum is the answer we get when we add things. So like 5 plus 3 equals 8, right? The sum would be 8, right? The difference between the difference has to do with the answer we get when we subtract. So if I had like 10 minus 3 equals 7, 7 would be called the difference, right? So it's the answer we get after we subtract. Product, that term, word, is used to mean the answer we get when we multiply, right? So if I had like 3 times 2 equals 6, then 6 would be the product, right? And quotient is the answer we get when we divide. So if I had like 10 divided by 2 equals 5, 5 would be the quotient, right? So we want to be careful with these because if we say something like twice the sum of x and 5, right? This means 2 times the sum times the answer. So I have to put this in parentheses, right? So we end up getting 2 times, and then the sum is of x and 5, so it'd be x plus 5, right? So it's twice the sum. This part here is the sum, right? So it's like an object, right? So you want to pay particular attention to how it's worded when you see sum, difference, product, quotient, right? So in other words, when you see sum, difference, product, quotient, it's helpful if you put parentheses around that and then input what the sum, difference, product, and quotient is, and symbolically, and that will protect you, right? Because that's not the same thing as if you just wrote 2x plus 5, right? These are not equivalent, right? 2x plus 5, if we distribute this, gives me 2x plus 10, right? I have to take the 2 times x and the 2 times 5, and so you can see that those are not equal, right, to each other, right? And so with these phrases, if I wanted to write these verbal expressions into variable expressions, right? The sum of x and y is x plus y. The difference between x and y, so when you see the difference between, the order stays the same. You just write x minus y. The product of x and y is x times y, or we can simply just write xy. Right? And then the quotient of x and y is the answer we get when we divide, right? So we're taking x divided by y, right? Or you could write it as a fraction, x over y, right? All right, so on the next page, I have an example, example 1. So we want to translate what we're given into a variable expression, right? So in other words, we want to rewrite it symbolically, right? We want to take it from the word form and put it symbolically. So we're told, right, we're taking the total of, right? So when you read the total of, you should be thinking addition, right? And then so what's coming next is it's telling us what we're adding, right? So how we know what we're adding is going to be joined by the word and, right? That's where the plus is going to go, right? The plus sign in um, in this symbolically, right? So what we're adding is these two things. Oops. 5 times b and c, right? So I kind of put parentheses around those to denote those two different objects, right? So 5 times b we can show as 5b, and I'm adding this with c, right? So the total of 5 times b and c reads as 5b plus c, right? Symbolically, right? So part B says the quotient, right? So this word, I should be thinking division, right? That's what I should be thinking. So then I'm looking for that word and, right? That's going to show me the two things I'm dividing, right? So I can go ahead, and if I wanted to write symbolically, I could write a division sign, right? So what I'm dividing is 8 less than n and 14, right? Those are the two things that I'm dividing. So 8 less than n, this is, remember we just went over less than, that's where the order switches, right? So you're actually going to write that as n minus 8, right? I'm going to put that in parentheses so that way order of operations holds true, right? Because we're taking two objects and dividing them by one another, right? So my first object is n minus 8. The second object is here, which is the number 14, right? And so since the denominator just has one set of parentheses, I could actually, get rid of those parentheses and that would be fine, um, right? You could also write this as a fraction if you wanted. You could write this as n minus 8 over 14, and that would be perfectly fine, right? So either one of those. Right. So the next one is part C, which says 13 more than the sum, right? So when I'm reading this, 13 more than the sum, right? I'm thinking we're going to have 13 plus some sum, right? So I'm going to be adding two things together. And those two things are going to be grouped by the word and, right? So the first thing I'm adding is 7. The next thing I'm adding is the square of x, right? So this would be 7, and the square of x would be x squared, right? So we get 13 plus 7 plus x squared, right? And the 7 plus x squared is in parentheses, right? Good. So now that we've had a little bit of practice with that, let's try some more of these. So with example 2 and 3, we're just told a number, right? Instead of us being told what the number is, we're just told a number and the number, right? So these look a little different. So you could use any variable you wanted for a number. Like I know the textbook likes to use an n for a number. I generally like to use just the generic x, right, to mean a number. Oops, write that a little nicer here. Don't have a lot of room. So let's use the pound sign for number there. But you could use, whatever you wish, right? You could use p, s, whatever variable you want to use. Well, personally, I try to avoid using s if at all possible, just because s kind of looks like a 5 sometimes. But you might be able to distinguish those depending on how you write your s's and 5s, right? So what we're told is we want to translate a number multiplied by, right? So a number multiplied by, right? So immediately what that tells me is I have x times something else. And then what we're multiplying it by is the total of, right? So that tells me I'm going to be adding two things. And I need to put parentheses around that, right? Because the number is being multiplied the total, right? So this total is like an object, right? So then what's inside the parentheses comes next. So the total of, so we have 6 and, so that tells me where my addition sign goes. The cube of the number, right? So notice it says the number, meaning referring, implying that it's the same number, right? So we're going to use the same variable again, right? So I would, in the total, in the sum, we would have 6 and then the cube of the number would be x cubed, right? Because we're using that same number, right? So in other words, what you should have is x parenthesis 6. Oops. 6 plus x cubed. And that would be your final answer. All right. So example 3 says translate the quotient of. So the quotient of, you should automatically be thinking division, right? So I'm going to be dividing two things. And then what are those two things? So the quotient of twice a number Right, so twice a number is one thing. Where the word and is telling me where that operation's going, right? The division. And then the difference between the number and 20, right? Those are the two objects I'm dividing. So twice a number would be 2x. And the difference between tells me I'm subtracting, right? So the difference between the number and 20, right? So that would be x minus 20. So if you refer back to that chart, when you are told the difference between, though you keep the same order in that case, right? So we have 2x divided by x minus 20, right? And keep in mind, if I didn't have these parentheses here, this would read as two separate things, right? Another thing you could do to avoid, if you don't like using the parentheses, is to set it up like a fraction, right? So when I write 2x in the bottom and x minus, or in the top, rather, and then if I write x minus 20 in the bottom and the denominator, that reads the same way, right? Because remember, this fraction bar is a grouping symbol, right? So these two things mean the same thing. They're equivalent. All right. So that's all for objective 1. Objective 2 is we want to do the same thing still. We want to translate the verbal expression into a variable expression. But then let's simplify the result if we can, right? So practicing the skills that we've been building up to, right? So like last section, we did simplify using properties of numbers, right? So example 4 says translate and simplify. So we have the total of, right? So the total of should immediately make me think addition, right? So I need to identify my object. So 4 times an unknown number is one object, and is where the addition sign is going to go. And then twice the difference, this is my other object, right? So maybe I'll leave those sides open to help you think if it would all be one. I just ran out of space, right? Because I had to go down the next line. Um, so the total of, so I know I'm going to have plus, and then I'm going to have two objects in here. So 4 times an unknown number is 4x, and then twice the difference, right? So that tells me I'm taking 2 times the difference, right? I'm going to be subtracting two things, and those two things I'm subtracting are the number and 8, right? So that would be x minus 8 inside of here, right? So this is what we get for translating those words into symbols, right? And so it turns out that I don't actually need these parentheses that I'm putting arrows on. It doesn't change the meaning of the expression if I remove those, right? So I'll go ahead and do that just to clean this up a little bit um, to make it easier to work with, right? So now what I could do to simplify this is I could use the distributive property and distribute the 2 through, right? And if you want, we can change this to a plus negative 8 to make that a little more cleaner with our signs, right? So this would equal 4x plus, and then we would have 2 times x plus 2 times negative 8, right? So simplifying this, that would give me 4x plus 2x, and then plus 2 times negative 8 is negative 16, right? So then now what I can do is I can combine like terms, right? So 4x and 2x are like terms, so I could write down 6x, and then I would have plus negative 16, right? Which, to simplify this even further, I could just write this as 6x minus 16, right? So remember, simplifying, we're trying to write the least amount of symbols, so that would be one less symbol than the previous line. right? So 6x minus 16 would be your final answer, right? So we're translating and then simplifying, right? So this part is what we got first of all for translating, and then we simplified it down to get 6x minus 16. Right, so we're practicing a couple of skills here. Right, so then another one similar to this, example 5, it says translate and simplify again. So we want to translate the difference between. So when you see the difference between, you should be thinking subtraction, right? So now let's identify my object. So I have 5/8 of a number is one object. Where the word and is, right, that's where my subtraction is going to go. And then 2/3 of the same number is my other object, right? So those are the two objects I'm subtracting, right? So I have an object minus another object. The first object is 5/8 of a number, which would be 5/8 times x, if I want to use x for a number, right? So whenever you see the word of, that means to multiply, right? So of equals multiply. And is, if you ever see is in a in a verbal expression, that's going to mean equals, right? So you probably have seen these before, especially if you've done like proportions and things before, right? So 5/8 of a number is 5/8 times x, right? Of a number is referring to a variable. So then 2/3 of the same number is 2/3 times the same letter, which is x, right? So whenever we repeat the same variable, it's implied that we're talking about the same number then, right? Because we're using the same variable to represent that. So if it were a different number, we'd want to use a different variable then, right? So, here the parentheses have no real meaning here as well, because we would multiply before we subtract. Um, so we don't actually need those parentheses, right? And I also don't actually need the time symbols in between the fraction and the variable x, right? Because it's implied if I have a coefficient in front, right, that it's multiplying, right? So I could clean this up and write this as 5/8 x minus 2/3 x. Right? So we're subtracting fractions, right? So we want to subtract 5/8 minus 2/3 in order to simplify this down. Um, so we need to have common denominators, right? So an easy common denominator, which is actually the least common denominator as well, the LCD, is 24, right? So if I take 3 times 8, that gets me to 24. So if I take 5/8 and I multiply it times 3/3, that will give me a common denominator of 24. And then for 2/3, I need to multiply by 8/8. Right, so I'm just writing that in like so, right? And these are still equal, right? Because 3/3 is just 1, and 8/8 is still 1. So I'm just multiplying the first thing times 1, and then minus, and then that thing times 1. So it's just going to be equal to the same thing, right? Because the multiplication property of 1 just gives me, if I take 1 times a number, just that number back, right? So we didn't change any value here, right? So it's still equal. So now if I simplify this, I multiply straight across, right? So 3 times 5 is 15. And then 3 times 8 is 24. So I would have 15/24x minus, and then I multiply straight across again, right? So 8 times 2 is 16. And then 8 times 3 is 24. So I get 15/24 x minus 16/24 times x. So now I have common denominators, so I can subtract those, right? So I would take and subtract their numerators and keep the common denominator, right? And I'm subtracting these coefficients because these are like terms, right? These guys are like terms, right? So remember, like terms have the same variable factors, right? In other words, the same letters with the same exponents. So I can simplify this further. So 15 minus 16 would give me -1, right? So this would be -1 24th times x, right? So -1 24th x would be my final um, answer here, right? So we translated and then simplify, all right? So now I'd like to work through objective 3, which is working through some applications of translating, right? So example 6, we're told that the length of a swimming pool is 20 feet longer than its width. Express the length of the pool in terms of the width, right? So in other words, if you want to draw a picture, a swimming pool is typically rectangular, and it tells us a length and the width, so it makes sense that this would be a rectangle, right? So we have length and we have width, um, and so and this is my swimming pool, right? And so what we're told is that the length of a swimming pool is, right? So remember, is means equals. So the length of the swimming pool is or equals, and then we're told 20 feet longer than the width, right? So if something's 20 feet longer, that would be the same thing as 20 plus the width, right? If that makes sense. 20 feet longer than the width would be 20 plus the width, right? And so we want to write this in a way where we're using a variable, right? So maybe the most natural thing to do would be to let W equal the width, right, of the swimming pool. So in other words, the width is equal to W. So the length would be equal to W plus 20, right? Because the length is whatever the width is and add 20 to it, right? So notice we were able to represent both dimensions with just one variable, right? So then the last example in the notes is example 7. So it's another application. So it says an investor divided $5,000 between two accounts, one a mutual fund and the other a money market fund. Use one variable to express the amount invested in each account, right? So if I have $5,000 and I split it into two different accounts, right? So I'll draw like this diagram here to show. I'm going to put some of the funds into a mutual fund, and then the remaining money is going to go into a money market fund, right? So let's say I put X dollars, right? I guess I wrote dollars, so I don't need the dollar sign. If I put, let's say I put X dollars in the first account, the mutual fund, then how much money would I have left to put in the money market fund, right? Well, that wouldn't that be just my total, whatever that total is, minus the amount I put in the mutual fund, right? Because I'm only have these two options, right? I'm putting, all this money, the total, into one of these two accounts. So I could write this symbolically, right? Because the total we know is 5,000, and the mutual fund, I'm saying I'm putting X dollars into there, right? So that would be 5,000 minus X, right? So in other words, we could, say let X equal the amount that we put in the mutual fund, right? So this is a typical thing that we do in mathematics is we define what our variable is, right? So notice I did this, like up here as well at W equal width and so forth. So that way it makes it clear when I'm introducing a variable what it represents. right? So I'm letting X equal the amount in the mutual fund. So 5,000 minus X is equal to the amount that we put in the money market fund, right? All right. So that's all I have for this section. So make sure you let me know if you have any questions. Thanks.